Hello, everybody. Welcome back. Today we're going to be looking at Unit 3.6, which is all about deviations from the ideal gas law. So let's get started. So let's start off reviewing just a little bit of what we said in our last lesson in 3.5 about characteristics of an ideal gas. And two of those characteristics include that ideal gases are said to have negligible volume. So to think of each gas particle almost as like just a single point. Another characteristic was that these particles exert no forces on each other. Okay, well, I hate to burst your bubble. I don't know if this is like, finding out that Santa Claus isn't real, but real gases are not ideal, okay? Real gases do have some volume to them. An atom has volume, and they do exert some forces on each other. To be specific, real gases, we've talked about this before, real gases exert intermolecular forces on each other. And so real gases do not obey ideal gas behavior. So let's look at a question that you could possibly see on maybe a multiple choice question or something. Which gas deviates the most from ideal behavior? Okay, and this is a little bit of review. Okay, the one that will deviate the most from ideal behavior will be the one that has the greater intermolecular forces. Okay, so let's review a little bit. CH4, methane, that first compound, is a completely non-polar molecule. So it has London dispersion forces. It experiences London dispersion forces only. Ammonia, that's the other compound. It's a covalent compound, so it definitely experiences LDFs. If you were to draw out its Lewis structure, you would see that it is polar, so it experiences dipole-dipole attraction. And because it has hydrogen and nitrogen, ammonia also experiences hydrogen bonding. So ammonia is experiencing the stronger intermolecular forces, which is going to cause it to be the gas that deviates more from ideal behavior. And if you're wondering, what would make it deviate from ideal behavior, if the gas particles are held more tightly together, like they are in ammonia, they're not going to strike the side of the container as often as maybe the molecules of methane will. And so the pressure predicted by the ideal gas law, PV equals nRT, isn't going to be quite accurate for a gas like ammonia. Okay, so that's the reason why. The best conditions that we can get to making a gas behave in the most ideal setting is by having it at high temperature and low pressure, okay? And if you think about it, think about the example we just did, ammonia, which experiences all three intermolecular forces. Its particles are held relatively tightly together. If you raise the temperature high enough, that's going to cause the particles to move at higher speeds, and intermolecular forces are going to become less and less of an issue. So high temperature, low pressure is the best situation we can get to having a gas behave in the most ideal way. Okay, now if any of you are wondering, well, if the ideal gas law isn't true for real gases, why do we use it? It's a good enough approximation for our calculations. For those of you that go into some sort of scientific career, maybe chemical engineering or something like that, you will have to take into account real world conditions, and the calculations are much, much more complex, but I'll let you enjoy that later in life. So just to wrap up here, guys, I have a little memory trick to help you remember that the best, most ideal conditions are at high temperature and low pressure. Can you remember the phrase hot lips? HT, high temperature. LP, low pressure. If you can remember hot lips, you can remember the best, most ideal conditions. Okay. And then one bullet point up, which gases are going to be the most ideal? The ones with the least intermolecular forces. So the more forces something has, the less ideal it's going to be. So this was a quick one today, but those are important concepts to know about, how real gases behave. So I hope you've learned a little something, and I look forward to seeing you next time.